Okay, so here's where we were last time. We were talking about Gauss's divergence theorem, sometimes called the divergence theorem. We hadn't really worked our way up to the theorem yet. But what we did talk about is, again, laying some of the groundwork. There's certain conventions and observations that need to be made before we can actually get to stating the theorem. So, first of all, again, the word boundary, loaded word, now no longer means just the edge, right? It means that edge, but with an orientation, a specific, precisely conventional orientation attached to that boundary surface. And again, the convention is this: away from the solid. Okay, so we talked about some examples last time. Excuse me. So next observation: all of these theorems that we're talking about, the Gauss's divergence theorem, Stokes's curl theorem, Green's theorem, etc., are all about accumulating quantities. Right? Even back to the fundamental theorem of calculus. That's a statement about an accumulating quantity if you look at it the right way. Change is an accumulating quantity. So anyway, for the context that we're in, looking at three-dimensional solids in space, the accumulating quantity is boundary flux. So specifically then, for any three-dimensional solid, such as, let's look at what I've got called R1 here. There's a three-dimensional solid. The quantity that I want to associate to that three-dimensional solid is looking at the boundary on each piece of the boundary, computing the flux. All right, so there you go. Outward oriented, of course, boundary flux. That's the quantity we associate to that solid. So we made the argument last time that boundary flux is an accumulating quantity. Okay, and that's when we ran out of time. So I will, though, real quick, just while I've got it open here. Here we go. There we go. Point out the analogy between, look at the picture here in which we argue that boundary flux is an accumulating quantity. And now go back over here to the discussion of Green's theorem, and you see the Green's theorem picture where we argue that, in that case, boundary circulation is an accumulating quantity. And what you notice is there's a lot of analogies. In both cases, when you sort of cut, in that case, your area, in this case, in this case over here, your solid, when you make these cuts, you introduce new boundary, right? But that's part of the boundary of both sides, and one oriented one way, as part of the boundary of the left side, oriented one way, as part of the boundary of the right side. Again, I keep forgetting to switch colors. As part of the boundary of the right side, oriented the other way. And in both cases, because of these opposite orientations, they cancel. So the analogy is very strong. It's morally identical argument applied just now in sort of a different context, not looking at circulation on areas, but looking at boundary fluxes on solids. Okay, so strong analogy. Okay, and that's where we left off last time. So moving along, I'm going to make the same case now that we have an accumulating quantity but we've made before a couple different times, and that I claim really is a general point. When you have a quantity that accumulates over interiors, you might say. So in this case, a quantity that accumulates over the solid. In this case, with Green's theorem, a quantity that accumulates over the areas. When you have an accumulating quantity, that means that the quantity in question can be thought of as having locations. Right? Now, it seems weird, and let's make the case for why this is weird, looking at this solid here. If I were to ask how much of this boundary flux that I, of course, compute on the boundary, how much of that boundary flux is happening, let's see, I think I need to switch to pencil here, is happening on this boundary. It's tempting to say, what a preposterous question. right? The little purple boundary there isn't even part of the green boundary, right? They're completely different surfaces, but this is a misdirect. When you talk about this accumulating quantity, namely in this case boundary flux, it's something that we associate to the solid. So I shouldn't be looking at the boundary of the big region or the boundary of the small region. What I should be asking instead, same question asked what I'm going to call more appropriately, would be how much of the boundary flux that I associate to this solid is happening inside of that solid. And now all of a sudden it becomes a perfectly straightforward and reasonable question. How much of I've got this stuff, I've got this okay, it's called outward oriented boundary flux, whatever, but I've got this stuff that's spread out throughout the green region. How much of this stuff spread out throughout the green region is in the purple region? Very, very simple question to answer. You just compute how much of that stuff there is in the purple region. That's how much of the previously noted stuff in the green region is happening in the purple region, right? If it were mass, this would be a trivial question. If it were ants or, flies or mosquitoes or whatever else, anything that's distributed throughout a solid, very reasonable question. So don't fall for the red herring that we perceive this particular quantity on the boundary. That's a misdirection, right? It's the fact that we perceive it on the boundary is not the point. The point is that it is actually associated to the solid itself. Okay. All right. So this accumulating quantity, and again I repeat, all accumulating quantities behave like stuff, and therefore you can treat them like stuff, like mass, for example. Because algebraically they behave just like stuff. All right, so with that point in mind, we can talk about density. Right? If we got a stuff, flux is a stuff. Well, in the same way that we can talk about mass per unit volume. Now, of course, the mass is distributed over the volume, so it's a weird picture. But anyway, we can talk about mass per unit volume because mass is a stuff. I can ask how much mass there is inside of that volume. Likewise, I can talk about flux, namely boundary flux on this region, and compare that to the amount of volume in this region. And again, we get this kind of messy picture because they're both taking up the same space. And so just to avoid the messiness, let me indicate the volume, where of course the volume is, and I'm going to revert to this, what I've previously called a misdirection of thinking of the flux as being on the boundary, just to make the picture look better. Right, just to avoid that confusion in the picture. So boundary flux per unit volume. Very reasonable thing to define. And in the same way that we referred to this, colors again. In the same way that we referred to this as being mass density, because the quantity is mass. Likewise, this we refer to as flux density, because the accumulating quantity in question is flux. Thus the name flux density. By the way, very common term. And I think I mentioned this back in chapter 3. But when I was in college physics classes, I heard the term flux density at least as much as I heard the term divergence itself. So anyway, very natural term, very common term. And let's see here, just to clean up my picture. Now, there it is, flux per unit volume, aka flux density. And here's the formula for it. Again, now I could derive this formula, but that would take up class time. It's details. It's a brute force computation. I don't personally find it to be all that illuminating. If you want to see it, feel free to come to office hours. I'll be happy to show you. It's in the book also. Yeah, like I say, it's just details, really. So that's the formula, though, that allows you to compute this thing called flux density, otherwise known as divergence. Name you'll recognize from chapter 3. very naturally denoted as div for obvious reasons. And we've previously noted also sometimes, not obviously, but very elegantly referred to as del dot. Right? Again, very common. This is a very common notation. This is a very common term. So be prepared to see all of those. Okay. So, cool. Now, we've made previous comments about, let's see here, let me hit that button, about densities. And let's see, I gotta scroll down to where that is. Yeah, here we go. So in the same way that derivative can be thought of as change density, and derivative also explicitly points to and tells us where change is actually happening, right? The density is telling you where the accumulating quantity actually is. The bigger the density, the more of that accumulating quantity is in that vicinity. And analogously, circulation density, Green's operator, tells us where there's more circulation. And we previously saw in the two-dimensional context that two-dimensional divergence tells you where the flux is, right? Where the flux density is greatest. Likewise, in the three-dimensional context, the three-dimensional divergence tells you where the flux is happening. Right, and so here we have a specific case of here's a vector field, and given a vector field, for any solid, we can talk about how much boundary flux there is on or in, depending on how you want to think of it, that solid. And so, okay, given that vector field, is there more flux being created at this point or at this point? Okay, well, no problem. Just compute the divergence at those 2 points. Divergence, aka flux density, will tell you, by virtue of which is bigger, where more flux is being created. That's what densities do. Right? So that's a nice point of view on divergence. It tells you where the flux is happening or where the flux is created in the interior. Even though, of course, we measure it on the boundary, obviously, right? Again, red herring. Divergence tells you where it is and where it's happening. Okay, so we have all of the necessary tools now to put it all together to make our big theorem. Sort of a 3-step process. We've identified outward-oriented boundary flux as being a stuff, as being a quantity that we're going to think of as associated to a solid. Right? We give it a name, we give it a notation, capital Phi for flux. Right? Next observation. It's an accumulating quantity. The whole of the sum of the parts. I can chop up that solid into a bunch of little, teeny tiny little solid pieces. And the total flux is the sum of these individual pieces of flux. Previously discussed. And lastly, there's an associated density. And so how much flux is there happening on any given little piece? Well, density times volume gives you flux. Now, notice this 3-step process here is really, really similar to the analogous sort of 3-step process. Here we go. Analogous sort of 3-step process that we did here for Green's theorem. Right? It's really the same idea. Strategically, structurally, it's the same exact idea that created Green's theorem. It's just that we're applying it in a 3-dimensional context with a different accumulating quantity, and so we get a different result. This result that we end up with here, very powerful result. It's called the divergence theorem, or Gauss's theorem, or Gauss's divergence theorem. Take your pick. All understood to refer to this. And what's really shocking about it is, like Green's theorem, it allows you to compute one kind of an integral with a totally different kind of an integral on in fact, importantly different domain, right? So if you want to compute a flux through a surface, this is an opportunity to compute that flux with a triple integral. The catch, well, there's 2 catches. This doesn't apply to just any old flux. It has to specifically be a flux through a boundary. It's got to be a boundary. That's the stick. That's the catch. That's the asterisk, right? The fine print is that this only applies to boundaries specifically. And then don't forget, of course, as well, you have to take the divergence of your vector field to get your new integrand. All right, let's see an example. Okay, if I can. Here we go. All right, so here we have S. It's an inward-oriented unit sphere. Perfectly reasonable surface. Right, and I've got a vector field, whatever. Some big, nasty, ugly vector field, and I want to compute the flux of that vector field through this given surface. Everybody on board? See what the question's asking. Let's just take a quick moment to speculate on how we would do this. If we were to take the old, classical approach to this, we would have to say, okay, well, I guess I'd better parameterize that sphere. But again, this is a really bad plan. Parameterizing the sphere means that X is going to be a bunch of nasty trig, and so is Y. Going to be a bunch of nasty trig, and so is Z. Maybe not quite as much, but still trig. So doing that would turn this into a pretty brutal integral. Right? If we were to do the whole parameterize and pull back thing, oh my gosh, it'd be a nightmare. Okay, so let's not do that. What we're going to do instead, you probably anticipate, is we're going to look at our surface and we're going to ask, hey, maybe I can apply Gauss's divergence theorem here. Now, tempting to say that sure, no problem. This is going to distract me. Let me erase all of that. Yeah, cool. Want to compute a flux? Let's compute a triple integral instead. But remember the asterisk, the fine print. I need my surface to be specifically a boundary of some solid. And again, this is not a subtle point. This is not uptight mathematicians being worried about formalities. No, it has to be that our surface is a boundary of some solid, because that some solid is the domain for the triple integral. If your surface isn't a boundary of a solid, then there is no solid over which to do your triple integral in the first place. It's not that the theorem doesn't apply, it's that there is no theorem if your surface is not a boundary. Right? Is everybody comfortable with that? Right. So huge point. It's got to be a boundary. And as written here, our surface is not a boundary. It doesn't follow the rules with orientation. It's not going the right way. Now, flashback. Let's see here. Flashing back to when we were doing Green's theorem, our very first time with Green's theorem, we had a curve that was oriented the wrong way and therefore was not a boundary. And how did we deal with that? Well, we just recognized, okay, well, look, it's just an opposite orientation on something that is a boundary. And so we noted that, but that's other than the minus sign on the orientation, this is literally a boundary of that disk. And so we're going to make the analogous argument over here. We're going to observe that, well, this is just the opposite, just the opposite orientation on that outward oriented sphere, which is exactly a boundary. That is perfect textbook boundary of that yellow ball. Is everybody with me? So cool, you have been asked to compute the flux on that green surface. We recognize that it's off by an orientation and thus a minus sign compared to the flux through this dark blue ball. Is everybody with me? Recognition of the minus sign because of the orientation issue, and now it's all over. But the celebration. Let's see here. Point being that surface is a boundary, and the divergence theorem tells me how to relate a boundary flux to a triple integral over the interior. So there's where we apply the divergence theorem. Everybody good? Okay, and don't forget that minus sign. That minus sign keeps progressing on through, right? So this minus sign continues along. Now we have a triple integral to compute, and just to keep life simple, let me erase all that. We're going to have to compute the divergence of this vector field, right? So we got to take that vector field, compute the divergence. This is just a little bit of calculus, right? A couple of partial derivatives. Make sure you're good with, of course, all those partial derivatives. Make sure, of course, that you're clear on what the formula is for divergence, right? It's the x partial of the first component, y partial of the second component, et cetera, et cetera. It's the sum of those three terms. By the way, a very common mistake that I see all the time is students will put commas here instead of pluses. This is a really, really important mistake. That's an error of type. Divergence, you'll notice, is a scalar quantity. If you write it as a vector, it's not even the right kind of critter, right? So very careful on that point. This is divergence. It's not, like gradient or something like that. Okay. So that being the case, we compute the divergence. The divergence ends up being this nice little, easy little formula right here. And now, all together, instead of computing a really ugly flux, now instead we're just going to be computing a pretty straightforward triple integral. It's really not that bad. And now again, it is a triple integral, and it is over now a ball, right? Solid ball. I probably would use spherical coordinates here, and you might be worried about, again, massive trig or massive square roots if you use rectangular coordinates, all of which is a little ugly and annoying. But sometimes you get lucky. And by the way, not just when you use the divergence theorem. Any time that you transform one computation into a different computation, there's always the potential that there will be good news, right? You get lucky with that new calculation compared to the old calculation. Here, I can turn this integral with two terms into two separate integrals, and individually, these two separate integrals are easy. This one is zero by symmetry. Make sure you can check those details. You want to make sure you're clear on why that integral is zero by symmetry. And this integral is an integral of a constant. Tell you what, just so I don't forget it, let me include that minus sign. Integral of a negative of the integral of a constant. And that is an easy integral because the volume is a barnyard variety, standard high school geometry formula. Everybody good? All right. Cool. So, so the divergence theorem, you can think of it a couple different ways. One is you can think of it as a tool for how to turn flux integrals into a different kind of computation that very often ends up being easier, and that's nice. It's also really useful in sort of conceptual ways, so I want to talk about some physical examples, some real-world physical scenarios, right, that I think are great, what you might call metaphors, or manifestations of the divergence theorem. So here I'm going to start with probably my favorite one these days, and that is a light bulb. So if you have a light bulb, and there's light bulbs all over the place, right? And what that is there's an actual hot spot, a little LED in most cases these days, let's hope, where all the light's coming out of that one little spot. Right? Now, the light is coming out of that one little spot, but then the resulting photons, the little particles that communicate light, all of those little photons are flying out, right, in all different directions, like so. right? So we have a flow of a fluid. We have a vector field then representing that flow of that fluid. All right, is everybody with me? Okay. Now, you'll notice what I've drawn here for the vector field is not a bunch of vectors of constant magnitude. How come this vector here is shorter and that vector there is longer? Speed of light is constant, right? Shouldn't those vectors be the same length? Answer, let me remind you, we don't always use velocity to represent a fluid flow, right? We sometimes use, for really good reasons, density times velocity. And so the thing is, when you are near the light bulb, the photon density is greater because you're closer to where the photons came from. They're kind of packed in closer. And then the farther you get out, the less photon density there is as you go out that direction. So that's why these arrows are shorter. Is everybody happy with that? Okay. All right. So, now a couple of observations. There's a couple of specifics about this fluid flow, I'm going to call it, that it's important to notice. This is a fluid that's being generated. That's what light bulbs do. They create photons, right? It's not like there's a limited supply of photons inside of your light bulb and it's shooting them out and diminishing its supply, right? The photons are not in there. They're getting generated by the light bulb. Okay. Now, another observation about this fluid, important to note, is that in any given location, photon density is constant. It's what we call a steady state flow because we're not running out of photons or collecting photons anywhere, anything like that. The density just doesn't change over time. Okay. Not all fluids are like this, and not all fluids are like this. Okay, so let's imagine what would happen if we were to take the divergence of this vector field, this flow of photons vector field, and I claim what would happen is if you were to compute that divergence at the location where the bulb is, you'd find that divergence is really high, really great. And this communicates a fantastic piece of information, right? So I've made this observation before, and I know it's a little abstract, but I have claimed in the past that when you measure boundary flux, right, you compute the outward-oriented boundary flux on this big sphere that we have out there, that, you measure that flux on the boundary, but that's not where it is. That's not where it happens. That's not where it comes from. It comes from the interior, right? And I've made the analogy that you think about a function that changes. The change happens in the interior. You measure it on the boundary, sure, but it actually happens in the interior. Well, this is a fantastic little physical example of how that's also true for flux, right? You visualize and compute flux on the boundary. Yeah, sure. But that flux, photons flying through that surface, where did those photons come from? They didn't come from the surface, right? The photons flying through that boundary came from the light bulb. They came from where the divergence is huge. The divergence is literally pointing to where the flux comes from in this very everyday, highly relatable physical scenario, right? So I think this is a really valuable example, if only to help you sort of digest the idea that these accumulating quantities may we compute them on the boundary, but they literally come from the interiors. You buy it? Okay. All right. Okay, let's talk about what is the divergence everywhere else. If I were to look at some location like right there, compute the divergence, well, you'd get 0, as it turns out. Kind of surprising, perhaps. Seems like with all that's going on, the photons going in various different directions, in different places, of course, and then the arrows are shorter the farther you get out. Yeah, it seems like there's potential for the divergence to be something complicated, but it's not. It's just flat zero. And again, very physically plausible. The divergence is zero because there's no photons coming from that location. Because that's not where the bulb is. That's not where the little LED is. At that location, photons go in, they fly right out. It's not the source of anything. So again, I think that's pretty, I'm going to put that in the win column for divergence. Divergence is telling us that this is not where the flux comes from. The flux comes from here, where the divergence is big. Okay, I think this is a really nice example for visualizing some of these ideas that we've talked about. Okay, now again, let me remind you, this is a fluid that is generated, but where density doesn't change. Now I want to talk about the exact opposite kind of fluid. Exact opposite kind of fluid. And here's my scenario. Suppose we have a balloon, basically, and there's a certain amount of gas in the balloon, and I don't know how much high school physics y'all have had, but here's a certain reality of gases, is that if you increase the temperature, the gas expands, right? And so I want to imagine a scenario where we have this balloon, there's a certain amount of gas on the inside, and that the temperature starts to increase, and the balloon starts to expand, right? Now, very importantly, there's no gas being created as the gas kind of flows outward, right? If the balloon is getting bigger and bigger, all those little pieces of gas are kind of moving outward, but we're not creating any gas. Same amount of gas. So again, it's the exact opposite of photons. Nothing's being created. And again, in opposition to photons, where the density is constant. Here, the density is decidedly not constant. If you have a certain amount of gas in a small volume, and if that same certain amount of gas starts to expand and be spread over bigger and bigger volumes, the density does change. The density is decreasing. Right? So, in both of these qualitative senses, this scenario here is a very different kind of gas. Very different interpretations, even though we draw a pretty similar looking picture. Okay. All right. So in this scenario, let's talk about a fixed sphere. Now, let's not accidentally conflate this with the balloon. This is a fixed sphere. You've got your balloon here that's expanding. We're looking at a fixed, smaller sphere on the inside. And let's think about what's happening as the gas expands. Gas starts to exit out of that sphere, right? And, well, here's the divergence theorem. Flux is the triple integral of divergence. And you can compute the divergence of this vector field without too much trouble. It's just a matter of writing it down, point being that it's constant. Okay, so let's make an interpretation then. What do I make of there being a flux through this sphere? What does that represent? Well, of course, it represents the gas leaving the sphere. How much of the gas is leaving the sphere? How much, therefore, mass of gas is no longer inside the sphere? Mass that was inside of the sphere is moving out to where it's not inside of the sphere. So if mass is leaving and it's not being generated to replace it, density has to be decreasing. So where is the density decreasing? How do we measure, how do we detect where the density is decreasing? And, well, that's what the divergence tells us. The divergence, being a constant, is an indication that the density is decreasing, in this case, uniformly, same rate everywhere inside of that sphere. And I think this also sort of stands to physical reason, right? I mean, if the balloon is getting bigger and bigger, the density is decreasing at a constant rate everywhere inside of the balloon, because that's how gases work, right? The density is uniform throughout the distribution. Okay. So we make different physical interpretations because we have a different kind of fluid. But notice we're making this interpretation with the divergence theorem, and we're making this interpretation with divergence as well. Okay. All right. Now, two different kinds of fluid. Now, very, very quickly, and I would love to have time to dwell on this little discussion here, but we really don't have time, and this is absolutely not Math 219, important stuff. But just an FYI, some fluids are kind of a combination of both. Sometimes fluid is being generated, like in light bulbs, and also the density is changing. Both. Right? And in that case, basically what we get is a sort of a combination of the above, and at whatever rate the fluid is being generated. Short version, when you generate fluid, there's two possibilities. That fluid that is generated either stays within your region, in which case you get an increasing rate of accumulation of mass inside of your region, or it doesn't stay inside of your region, in which case it leaves through the boundary and counts as flux. And so in this scenario here, where you have both of these features of the fluid, kind of a combination, again, of the two different kinds of fluid we've already seen, then you just have this relationship between these quantities, and you can divide by volume, and flux per unit volume is divergence. Mass per unit volume is density, and then if you have some indication of how and where the fluid is being generated, then you can use divergence to understand how densities are changing. So, anyway, I wish we had more time for that. Well, we don't. Don't worry about it. Okay, I want to talk about gravitational fields. Pretty standard vector field, right? Pretty standard force field, vector field representing forces. And you've probably seen previously the formula for the gravitational field created by a point mass. Never mind the fact that that's not a real physical thing, right? But it's pretty close, and it turns out that it works just fine in practice. And the formula for the gravitational field we saw previously, we write like this. And this is why we call it inverse square radial, right? Here's the inverse square part. And here's the radial part, because that's a unit vector pointing directly outward. Right? So inverse square radial, that's how gravitational fields work. Here's the really important observation. It turns out this is exactly structurally the same as a light bulb. Inverse square radial. Light bulbs are, the photon fluid flow that they create is inverse square radial. Just like gravity. Now, they're totally different things, right? Light bulbs are generating a fluid of particles that are flowing outward away from the light bulb. Gravity's, it's not a fluid, is it? Right? I mean, gravity's this mysterious action at a distance force thing, and it doesn't feel like they're the same thing. But it's, again, what an eyebrow raiser that these two physically different things are exactly the same structure. And the fact that they are algebraically the same leads to a real physical theory, which is that gravity is actually communicated by little particles that are flowing outward away from the mass, just in the same way that light bulbs emit photons that fly outward. Mass, so goes the theory, emits something called gravitons that fly outward. It's just a theory, right? And whether it's true or not is a long, complicated conversation. And whether it's even believed is a long, complicated conversation, as it turns out. But none of that matters to what we're doing. The point here is that whether it's true or not, gravity certainly behaves as if it's communicated by little emitted particles, kind of like light bulbs emitting photons. And these little particles are called gravitons. The beautiful fact, again, when you're doing physics of gravitational fields, perhaps in an engineering class or something like that, if you're doing physics of gravitational fields, just pretend, true or not, go ahead and pretend that gravity is created by mass shooting out little particles called gravitons. Then the fact that gravity and light bulbs have the structurally the same formulas is not weird at all. It's perfectly natural. They're the same things. Okay, all right. So what is this bias? It allows us to do this little calculation down here. I'm going to talk about these. There's kind of 4 equations here. Let's talk about the top one first. I'm going to start by looking at this constant right here. You see we have the same constant on both sides of the equation. Let's temporarily ignore that constant. After all, you're allowed to multiply a constant on both sides of the equation. That's not the mystery here. So let's first observe that what this top equation is saying then is that mass is a triple integral of density. Well, sure it is. Old news. No one's surprised at this fact. Mass is a triple integral of density. Multiply on both sides by negative 4 pi g for reasons that I'll explain in about 30 seconds. Okay, that's the top line. Now, next, let's talk about this equation right here. Keep in mind, mass creates gravitons. If you have a surface with mass on the inside, if that mass is shooting out gravitons, how many of those gravitons will leave passing through this surface? Well, all of them, right? There's mass in there and the graviton shoots out. It runs off to infinity. Of course it passes through and leaves the surface. It's heading to infinity, right? So the amount of gravitons leave, let me color code this better. The amount of gravitons that leave through the surface should be proportional to how much mass there is. More mass shoots out more gravitons, thus making more flux. So we expect there to be a proportionality there. Does that make sense to everybody? Now, what is the proportionality constant? The proportionality constant between the mass and the flux is that's a little calculation. It's not even a hard calculation. If this were a year-long class that would give me the 5 minutes I would need to do that calculation, I would totally do it as a reasonable calculation. But tough choices and all that, so I'm cutting it. And I'm just going to say, if you do that calculation, turns out to be that proportionality constant. So that's why I multiplied negative 4 pi g on both sides of the top equation. It's so that this left side equation would actually have the right constant. Okay, so we're almost done here. This is just an observation that mass is an integral of density. This is an observation that mass creates mass creates gravitons that create flux. Gauss's divergence there. So check it out. This little 3-step process tells us that integral is equal to this integral, and that this is true for all regions. Every 3-dimensional region, this is always true, and that tells us that these two integrands have to be equal. And this is a very powerful result. What this tells us is that gravitational divergence comes directly, indirectly, however you want to say it, it comes from mass density. constants involved as well. But the more density of mass there is, the more divergence of gravitational field there will be. And let me try to explain why this is a jaw-dropping equation. If you were to try to get this result directly without using really clever observations that, such as what we made here, this is a horrifyingly difficult derivation, because if you've got density, that means you've got mass in different places. This little particle over here of mass creates its own little gravitational field that is different from this little particle of mass over here that creates its own gravitational field centered at different locations. And if there is a density, if there's a distribution of mass, that means that there's trillions of little itty-bitty individual little pieces of mass all creating their own little gravitational fields. So this gravitational field right here is a absolute nightmare to compute. Absolute nightmare. Oh my gosh. I'm not even going to begin to try to compute that gravitational field, but I can compute its divergence basically effortlessly. So it's really, really powerful conclusion. And there's lots of situations in physics where this fact is indispensably valuable. So wonderful little result. Where did it come from? Who gets the credit for this fantastic equation? Well, the divergence theorem. This is the linchpin. This is what makes it. This is the cornerstone of the art. This is the nugget, the kernel. This is the essential ingredient that makes it work. So, wonderful application of the divergence theorem. Is everybody happy? Okay. Now let's talk about electric fields. You may notice this little arrangement of four algebraic objects and four equations looks a lot like this one up here. Lot like it, because electric fields, they're also inverse square radial. They look just exactly like gravitational fields. They point outward instead of inward. Fine, okay. So that's just a constant, right? That's the minus sign. No big deal. But structurally, they're inverse square radial. So all of the same arguments apply. And so we get this same powerful result. The electric field created by a distribution of charged particles, incomprehensibly impractical to compute. Couldn't begin to compute the actual electric field itself, but its divergence, boom, no problem. It's just directly proportional to this little thing called charge density, which is exactly what it sounds. It's total electric charge per unit volume. So, really nice fact. And those of you who are engineers are much more likely to be doing stuff with electric fields and electric charges than gravitational fields, because let's face it, on the surface of the Earth where we spend most of our time, gravity's a constant, and it's a pretty simple story. Electric fields, definitely not so much, right? Electric fields are weird and complicated in all circumstances. So, very powerful result. So, just to kind of connect all the dots, the light bulb metaphor that I think is highly relatable is the foot in the door to understanding gravitational fields, which I think are also pretty relatable. We have a good intuitive grasp on mass. We have a good intuitive grasp on gravity, right? I drop something, it falls. I mean, I've been familiar with gravity since I was a toddler, right? So light bulbs help us understand gravity, which helps us understand electric fields that you're going to essentially need for building anything that has to do with electricity. Nice little sequence of thoughts there. Okay. Any questions about any of this? Okay. So real quick, just a little bit of terminology. This is called one of Maxwell's equations. I'm sure you all have heard of Maxwell's equations. If you've previously studied them, you might even recognize this as being what I like to call Maxwell's first equation. Then there's also this. You may recognize this from Maxwell's equations, also known as Maxwell's first equation, because they say basically the same thing. The difference between these two is, in some sense, that one is a triple integral of the other. So very often this is referred to as the differential form because it involves derivatives, right? And this one is called the integral form because, well, it depends on how you look at it. You can think of this and or this as being computed with integrals. So anyway, they're very different looking individually as equations, but with the observation that one's just an integral of the other, we like to think of them as being morally the same equation. Okay, so the nice little cultural point. Okay, so that's Gauss's theorem. And move on now and talk about Stokes' theorem. Again, there's some setup that we have to do. We've been down this road a bunch of times at this point. I have to tell you what the deal is with boundaries. In particular, there is an orientation to be assumed when you talk about the boundary of now a surface in space. New geometric context, but I've got to talk about boundary. What do I mean by orientations? I'm going to have to talk about an accumulating quantity. Once I have an accumulating quantity, I'm going to make the case that, well, yeah, but that means that this is a physical stuff. I can treat it like a physical stuff because it behaves like physical stuff. And then I can talk about the associated density, and then I can write down a theorem. So we've done this dance before, right? Different details is all we're going to be seeing here. So let's think about those details, starting with the convention on boundaries. I emphasize this is arbitrary, but again, it's conventional, so it's not optional. It's this is the convention that we have to stick with, and the rule is this: suppose that you have a surface, correction, an oriented surface. Keep in mind what an orientation is on a surface. An orientation on a surface says which direction is the positive direction through that surface. Right? There's our surface. Now I want to talk about the boundary curve. If you have a surface such as this, here's a surface in space. The boundary is the edge of the surface. It's exactly what you think, right? But there's the question of which way do we go around the edge? The boundary being, let's see here, let's see if I can draw this without messing it up. The boundary is that piece of curve like that. Should I think of that piece of curve as going this way, or should I think of that piece of curve as going this way? Which is it? And there's a little bit of a complicated story here. It'd be nice to say, something simple like clockwise or counterclockwise, but the problem is clockwise or counterclockwise as seen from where, right? What you might call, from my point of view, as I'm looking at this piece of paper, I would call what my finger is doing clockwise, right? Going around clockwise. But as y'all see it, oh my God, as y'all see it, it looks counterclockwise. So clockwise, counterclockwise isn't really a meaningful concept in 3 dimensions. So we have to come up with something different. And there's a way to phrase this in terms of right-handed versus left-handed and stuff like that. But I ultimately think that there's an easier way to think about it. So I'm going to show you what I think is the easy point of view. And it's like this. The orientation on the surface. If you point your thumb in the direction of that surface orientation, the fingers of, right hand thumb. Very important. It's got to be your right hand. Apologies to the left-handed people. It's got to be your right hand, arbitrary convention. Thumb in the direction of the normal vector. Your fingers of your right hand want to bend in a certain way that points in direction of what I'm going to call a swirl. Now, which direction, in other words, on the surface you're rotating around that axis defined by that normal vector. That swirl sideswipes in a certain direction along the boundary. And that direction of the sideswipe is the orientation on the boundary. Is everybody happy with that picture? So, normal vector, thumb, swirl, sideswipe is the orientation. And I find that visually satisfying and geometrically satisfying, and in a situation where you have a surface like this, it's tempting to say, okay, well, yeah, but, wouldn't it be easy to just think about some little guy walking along the boundary, etc.? But what if your surface is oriented upside down? And then you have to imagine, okay, now my little guy walking along the boundary, well, he's upside down, and then you're going to find yourself being like, okay, so here now I'm walking along, and it's contorted and weird, right, if it's upside down. Whereas this scenario, if your surface is oriented upside down, no problem. Thumb points in the direction of the normal orientation, so I just turn my thumb down like this, and then I can just look and see which direction my fingers point. And I don't have to turn myself upside down or imagine myself upside down or whatever. So I think this is the easiest way to do it. Oops. I encourage you to think of it this way. All right, so there's the convention on orientation. We're back to thinking about boundary circulation, just like in Green's theorem. And I want to come back over here to, let's see here, let's go back to where we were doing Green's theorem, and you'll even notice that the picture is really reminiscent, right? When we were looking at boundary circulation in the context of Green's theorem, that and that, right? Same thing here. Now it's just that now we're looking at sort of what you might call swirls on a surface in space, as opposed to swirls on a, surface in the plane, aka just a region in the plane. But again, the pictures though, right? Really, really similar pictures. So accumulating quantity, because as in the case of Green's theorem, this cut edge is going to be part of the boundary of both D1 and D2, but with opposite orientations. Likewise, in this new context, this cut edge here is part of the boundary of both S1 and S2 with opposite orientations. So, really similar story, right? Everybody see what I mean? It's a really similar situation. It's just, it's floating up in space now instead, but practically identical pictures. Okay. All right. So, boundary circulation is an accumulating quantity. And again, that means that I can think of it as a stuff. I can think of boundary circulation as being distributed over the interior. Again, don't fall for the red herring suggested by how we compute circulation, suggesting that it's something that's on the boundary. It's not. That's an illusion. That's just how you compute it. Circulation is something you should think of as happening on the interior. That's where the circulation's happening. Right? And so to the reasonable question, how much of the quantity in question over the green surface is happening on this little blue surface? And no problem. How much of the stuff is in the blue surface? Just compute it for that blue surface. We're just going to compute the boundary circulation then around the boundary of that little blue surface. So I can think of, by this argument, I can think of this accumulating quantity as distributed over the surface itself, despite appearances of computation. So, it's a stuff, like anything else that you can spread over a surface like butter, right? It too is a stuff. So, which means that I can talk about its associated density. Right? And again, it's a hard picture to draw, but circulation being a stuff distributed over an area, I can very reasonably ask how much of this stuff, which again, for lack of sort of artistic options, I'm going to represent on the boundary, even though, again, we really shouldn't think of it that way. How much of this accumulating quantity called circulation is there per unit area? This is just a density. And it's what we call circulation density because the accumulating quantity is circulation, right? So, familiar, right? I mean, it's exactly what we wrote down with Green's theorem, circulation per unit area. It's just that now our area is floating up here in space. Still morally equivalent idea. Okay. Tedious calculation ensues to how do we compute what this circulation density is. Let me just skip to the end. Again, it would, I feel like it's not particularly helpful or instructional for Math219 to go through that calculation. Elegant and powerful though it is. But the big idea, though, is to understand what this expression means. This thing that I claim is circulation density is circulation per unit area. Is everybody okay? Everybody, again, noticing that it's the same story as with Green's theorem, different details. Okay. All right. Awkward. Notice that this depends on the surface. That's weird. Right? Previously, when you've had a density, it's been a function of location. You look only at the vector field. The vector field is defined based on location. So, how come here my density depends also on the surface, and specifically how the surface is oriented? Divergence doesn't have this property. Green's operator does not have this property. Single variable derivative does not have this property. This is unexpected and weird. We're going to come back and talk about that in a little while, time depending, maybe even later today. But for the moment, let me set that aside. This is just a doff of the cap to something that does need to be addressed. Until then, let's just run with the formula as it is. And here we go. Then we can write down Stokes's curl theorem. Again, you recognize the structure. I deliberately write these sort of derivations in analogous ways because I want to emphasize they are really literally analogous arguments. And so here we go. Just like with Green's theorem, we're talking about this quantity called circulation, which we have argued is an accumulating quantity. And if it is an accumulating quantity, then we can talk about the associated notion of density. Stuff per unit size, right? And there's the density that we computed above. So altogether then, we have ourselves a theorem. This line integral can be computed with that surface integral. And that's Stokes's curl theorem. Which, by the way, we could rewrite as usual. I mean, look at this, how convenient. That little combination, little n times ds scalar, that's exactly the pairing that we've previously called the ds vector. And I like this ds vector notation, a little bit more elegant, a little bit more compact. So with that in mind, then, let's re-visualize then. Stokes's curl theorem is this theorem right here. So a line integral computed with a flux integral. Cool? All right. Now, again with the asterisks, the catch, right? This cannot just be any old line integral. You got to watch out for this really dangerous point. This is not any old line integral. It's specifically, explicitly, we see, only a line integral over a boundary. It's got to be a boundary. Because, well, a combination of reasons. For one thing, the proof doesn't work otherwise, but I think it's a on its face persuasive argument that you've got to have a boundary of some surface, because that's the surface over which you would need to compute the corresponding flux. If your line integral is not over a boundary, there is no surface over which to even talk about a corresponding flux. So again, it's not that the theorem doesn't apply, it's that there is no theorem if your curve is not a boundary curve of some surface. Everybody see that point? Okay. It's a really big one, and I'll talk more about how that rears its ugly head tomorrow. Okay, so let's see here. Okay, here we go. So let's see an example. And this is just a sort of computational example. Suppose we want to compute this line integral. We got a vector field given. We got a curve given. In fact, the curve is already parametrized. That's nice. Again, hesitate before you follow the seeming implication of we have a pre-parametrized curve. I've been asked to compute a line integral. We've got a plug and chug option here. We could pull back through the parameterization a la chapter 6, right? And we could just straight up plug and chug and compute this line integral. But notice what a nightmare that would be, because x is cosine t and y is minus sine t, and you're going to have some ugly pieces in there, and that's all else being equal, not ideal. So this would be a hard calculation. Okay, so let's try to apply Stokes' theorem. We apply Stokes' theorem, which says if my line integral is over a boundary, then I can do stuff. So let's ask the question, is this curve a boundary? You got to be careful here, right? There's a temptation to say, oh, the curve is going clockwise, and I feel like curves are supposed to go, if boundaries are supposed to go counterclockwise. There's a temptation, if you inadvertently think of this as a two-dimensional problem, to say that no, this is not a boundary. But keep in mind, we're in 3D now, and in 3D, previously noted, we have this different rule for boundary orientations, and it's not about clockwise, counterclockwise. It's about thumbs and fingers and side swiping, right? And so, is this curve? Here we go. Is this curve a boundary? And it turns out, yeah, sure it is, no problem. It's the boundary of this surface right here. But wait a second, I can't just say a surface. It's got to be an oriented surface. Which way should this surface be oriented? Should it be upward? Should it be downward? Which one of these orientations on the surface makes the boundary satisfy the rule? And just to play the game, let's try what we can see is going to be the wrong answer. I know it's going to be the wrong answer. Let's just see why this is the wrong answer. Why can't I use up as the orientation on this surface? Well, because if I did, thumb, fingers would set up a swirl that would be going that way, which would sideswipe in this direction, whereas the curve that I'm given needs to go that direction. This upward orange surface orientation gives me the wrong boundary orientation. Yes?
In a problem, would the picture be given so we could see what direction the curve was going in?
I don't necessarily have to give you a picture. I can just describe. So sometimes I'll say, I've got different versions of how I've done this in the past, but one thing I could do is say, for example, that here's the curve, parameterized in a certain way. Oh, well, when you have a parameterization, that tells you an orientation right off the bat. Because in particular, as t increases, that takes you in a specific direction around that curve. So that implies an orientation. But even if I didn't have that, even if I just told you, well, it's the unit circle, sometimes I'll give you the orientation by telling you, okay, well, at this point, the orientation goes that way. Something like that. And then I'll leave it to you to draw your own picture. So you're right that I definitely have to tell you the orientation on the curve, but how I give you that orientation, there's a bunch of options.
Okay.
Is that satisfying? Okay. Good. Anybody else? Okay, so now let's try the other one. Let's suppose that our orientation were to go downward. Well, again, don't turn your head upside down, right? Just turn your thumb upside down. So thumb in the direction of our new candidate surface orientation. Think about what your fingers do. Your fingers then are going to swirl. They're going to swirl like that, which sideswipes in the correct direction. So there's our normal vector. Everybody on board? So yeah, cool. We've got a boundary. Stokes' curl theorem then tells us that as we have been asked for a line integral on a boundary of a surface, this curve being the boundary of that surface with this normal vector, Stokes' theorem tells me that the circulation, the line integral, is that flux integral. Everybody happy? Okay. Now, let me remind you. I've made this observation before, but when you're talking about, Green's theorem, the divergence theorem, now Stokes' theorem, all it does is it turns one kind of an integral into a different kind of an integral. It's not a magic wand, right? It doesn't just turn questions into answers. It turns one integral into a different integral, kind of like a substitution in a way. It's not a magic wand. It just turns a question that you don't know how to solve into a different question. And then you can hope that different question is something you do know how to solve, right? So that's the circumstance we're in here. We have now a new flux integral, and we have to ask the question, can I compute that flux integral? Well, curl for that vector field turns out really nice. The curl is just 002. So that's a big win, right? This ugly vector field has a really nice curl. Yeah. Cool. And let's see, we also, of course, have previously discussed that the normal vector is 0, 0, minus 1. And that makes our integral turn into what is, in fact, a pretty straightforward integral. We just have the surface integral of minus 2 over a garden variety surface. And so easy calculation and answer. What do you think? Everybody all right? Okay. Real quick observations. I made this observation back here that we'll make an interpretation later of what's the deal with our density, our circulation density, depending on orientation. And I made this up to be a really big deal that we've never seen before. I swept something under the rug there. In fact, we have previously seen a density that depends also on the orientation of the domain. And it happened with the fundamental theorem of line integrals. Right? So fundamental theorem of line integrals, very often we write it as this, right? But you can also think of it as this. And from that point of view, with change computed by this formula, the density, you can look back to our notes in 6.3, I think it was, wherever we talked about the fundamental theorem of line integrals. Our change density is gradient dot t. And so there's that same dependence on orientation of the domain. That same sort of like eyebrow raising, suspicious, hey, wait a minute, what's going on here, feature. right? And so all I did in that case was to kind of absorb that into a vector differential and then say, well, look, let's just reinterpret this whole thing as instead of thinking of stuff per unit size, thinking of size as a scalar, let's instead just, thinking kind of flexibly, open-mindedly, let's think of stuff per unit, in a sense, oriented size. That's what the dx vector is. It's telling you size, but it's also telling you direction. It's telling you an orientation. How is your little piece of curve oriented? What direction is it pointing? Right? And so stuff per unit oriented size, I argued as being an oriented density. So I referred to the gradient as being oriented change density as a point of view. Right? Now again, you got to think open-mindedly about size as being itself an oriented thing. So we're going to do the exact same thing now with Stokes' theorem, and here we go. Stokes' theorem you can think of either as this, or you prefer this. Take your pick, and sure, if you think of circulation per unit size, then here's your circulation density, and yes, there is that normal vector. Surface orientation is in there. That's weird. What's going on? Why do we have that? Well, let's just reconceive now of circulation not as being per unit scalar size, but per unit oriented size. And again, that's what the ds vector is. It's telling you how big your little piece of surface is, but it's also telling you how is that little piece of surface oriented. It's telling you by way the direction that it points how that piece of surface sits in space. So, in the sense that this is an oriented area, likewise this is an oriented density, and specifically an oriented circulation density, because that's what we're computing. So I think it's a really nice way to think about curl. It is a density of sorts. It's just that it's an oriented density, and in the same way that gradient, coming back up to here, in the same way that gradient has a magnitude that's telling you how steep the mountain is or how fast the function's changing, whatever you want to call it, and a direction that's telling you which direction is uphill, which direction is the function actually increasing in. Well, likewise, curl. This weird quantity curl. Also, its magnitude and direction tell you specific things. So the magnitude of the curl tells you how much the fluid is rotating, how much of are we talking about a really strong sort of, vortex, tornado, whirlpool of fluid, or is it a gentle kind of, slow rotation of the fluid? Right? In the same way that the magnitude up here tells you how much change is happening per unit distance, how steep is the mountain, likewise, this is telling you how much rotation. And likewise, the direction that it points is telling you around what axis is that rotation happening. And we're out of time, so we're going to have to pick it up from here next time, and we will talk about some more specific examples of this, and then take it from there. Okay, y'all have a good day. See you later.